In this video, I'd like to talk more about the partition function. In the previous section, 13a, we derived this Boltzmann distribution, which tells us that the population of state I over the total number of states is equal to this, where the denominator is what we call the partition function. Okay, so the partition function was defined to be the sum over this quantity for all states, j, where the energy of the jth state is epsilon j, and beta is 1 over kt. So if we know all of the energy states, which we can learn from studying quantum behavior and finding the quantum states for a system, then we can calculate Q. And Q is, the partition function Q is a very useful function. So let's talk about what it is and what it can do for us. Okay, so the first thing that I need to address is what's called degeneracy of states. Okay, so degeneracy of states means that some states might share the same energy. So we could have, they could have the same energy level. And these are called degenerate states. So we can define degeneracy, G sub I, as the number of states that share energy sub I. And notice that Q up here is a sum over all states. If we wanted to sum over all possible energy levels, we have to take into account that some of those energy levels may have multiple states in them. So with the degeneracy defined, we can write Q as the sum, this time over all energy levels instead of all states. And we'll label the energy levels with J, just like we did with the states. So it's the sum over all energy levels of the degeneracy times e to the minus beta energy. So this is a multiplicative factor saying that if there's one state at this energy level, this contributes one time. If there's two states at that energy level, then we get two of these contributing to the partition function. All right, so I'd like to talk about a special case, which is when the energy levels are all equally spaced. This is a special case, but it's going to illustrate the essence of the partition function. So our energy levels might look like this: 0, epsilon, 2 epsilon, 3 epsilon. So the spacing between each of these is epsilon. And we're also going to focus on the non-degenerate case, meaning there's only one state for each of these energy levels. So notice I can summarize this by saying that the energy of state I is equal to I times epsilon, where I starts numbering at 0. So when I is 0, we get 0. When I is 1, we get epsilon, 2 epsilon, 3 epsilon. Okay. So this is a compact way of writing this. And a compact way of writing, or a mathematical compact way of writing non-degenerate, is to say that the degeneracy of state I is equal to 1 for all I. So with that and this, I'm going to plug those into this equation here, where I'm summing over the energy levels. So I'm going to be summing over these energy levels. G in each case is going to be 1. Okay, so Q for equally spaced non-degenerate energy levels looks like the sum over J, e to the minus beta J epsilon, because epsilon J is going to be just J epsilon for these equally spaced energy levels. And just to remind us that we started numbering with 0, I'm going to put J equals 0 as our first and we'll go up to n however many energy levels we have, which could be infinity. All right, so let me write out this sum. So when j is 0, I have e to the 0, so I have 1. When j is 1, I have e to the minus beta epsilon. When j is 2, I get e to the minus beta 2 epsilon, e to the minus beta 3 epsilon, and so on. And remember that when you raise something that has an exponent and you raise it to another exponent, that's like multiplying the exponent. So I'm going to do the opposite of that, just so that we can see the pattern here. So I'm going to rewrite this as e to the minus beta epsilon squared, because when we raise this exponent to an exponent, we end up multiplying the exponents, okay, which will give us this. And the next term is e to the minus beta epsilon cubed, and so on. And so notice that this is a geometric series, right? This is the case for j equals 0, j equals 1, j equals 2, right? This is a geometric series where each term is the previous term multiplied by e to the minus beta epsilon. Okay, so a general geometric series we can write like this: x to the 0, x to the 1, x to the 2, x to the 3, all added together. And you may remember from calculus, this type of series are typically addressed in calculus 2, that we can write down the sum, even if it's an infinite sum. We can write down the total as 1 over 1 minus x. But this only works if x is smaller than 1. Otherwise, these terms would be growing without bound, right? And then this series would diverge. But if x is smaller than 1, then these terms that we're adding get smaller and smaller, and this series actually converges to 1 over 1 minus x. Okay, so if we compare that to the geometric series for q, we can see that x in this case is the thing that's raised by increasing powers, is e to the minus beta epsilon. So in our case, x is e to the minus beta epsilon. And if we think about this for a second, remember epsilon is the spacing between energy levels. So it has to be greater than 0. We can't have 0 spacing between energy levels. That would be just a single energy level with degeneracy. Okay, so the spacing of the energy levels must be greater than 0. Beta is also greater than 0, because beta equals 1 over the product of two positive numbers. So that means this exponent is always negative, and therefore x is going to be smaller than 1. So x is less than 1. So I can use this to calculate the sum of the geometric series that I wrote down. So q then is 1 over 1 minus, and x was this, e to the minus beta epsilon. So this is the formula for the partition function for the case of equally spaced non-degenerate energy levels that are spaced with energy spacing epsilon. And in your book, they call this the uniform ladder, because the energy levels look like a ladder that are with rungs that are equally spaced. And so this is the uniform ladder partition function. Okay, so let's use this partition function. So continuing with the equally spaced, the uniform ladder, what are the fraction of molecules in state I, where state I has energy EI, and this is at a given T, given temperature. Well, to figure this out, first of all, what we're looking for here is the number of molecules in state I divided by the total number of molecules. And this is the left-hand side of the Boltzmann distribution. So the Boltzmann distribution tells us that this ratio is equal to e to the minus beta epsilon I over q. Okay, so this is Boltzmann distribution. And since we're talking about a uniform ladder, then we know q. Q is 1 over this. So this is 1 over q. So this is going to flip back, and we're going to end up with 1 minus e to the minus beta epsilon in the numerator times e to the minus beta epsilon I. Okay, so this is because we used q for the uniform ladder. And just be aware that this epsilon has an I and this one does not, right? Because this is the energy level of the energy of the ith state, whereas this is the spacing between these. And actually, I can rewrite epsilon I as I times epsilon, like I did in the previous page. And this is what we call PI, the probability that you'll find a molecule in state I is given by this for the uniform ladder. So let's look at this probability of being found in state I as the temperature gets lower. So as T approaches 0, then since beta is proportional to 1 over T, beta approaches infinity. And if we look at this term, e to the minus beta epsilon, this is beta times a constant. Beta is going to infinity, so this is going to e to the minus infinity, which approaches 0. Which means that Q, which is up here, 1 over 1 minus e to the minus beta epsilon, if this is going to 0, then Q must be going to 1. Which means that PI is just going to be this over 1. Okay, so PI approaches e to the minus beta epsilon I. And so from this, we can see that as this energy gets smaller, if we're choosing I such that we're looking at some of the low energy levels, this number is going to be closer to e to the 0. Okay, so whereas if this was a bigger number, this would get closer to e to the minus a large number, which would be this whole thing is getting close to 0. So as epsilon I goes to 0 as it gets smaller, PI goes to 1. So this is actually exactly what we would expect, because here we're saying that as the temperature decreases, the probability that you'll find all of the any molecule in the lowest energy state where E equals 0 approaches 1. Okay, so this is another way of saying that all molecules will be in the ground state. And this is what we would expect as the temperature approaches absolute 0. Okay, what about the high temperature case? So that one's really interesting. And to do that one, I'm going to simplify this once more, and we're going to assume that we only have 2 states in our system. They're still equally spaced, of course, because there's only 2 of them. So let's simplify this to the 2-state system and see what happens. All right, so a 2-state system might look something like this. our lowest energy level is 0, and our next energy level is epsilon. All right, so let's calculate the partition function for this system. I'm going to go back to the original definition of the partition function, which is the sum over all the energy states. And there's only two in this case. So the first one is when I is 0, epsilon I is 0, so we just get 1 for the first term, plus the second term, epsilon 1 becomes epsilon, so I have e to the minus beta epsilon. And that's it for the partition function for this two-state system. Okay, now I can easily find the probability of finding a molecule in state I. That's going to be from the Boltzmann distribution. That is the Boltzmann distribution. And so that's going to look like e to the minus beta energy level I divided by Q, which is this, 1 plus e to the minus beta epsilon. All right, so now we have the probability of finding a molecule in state I, and we only have two states, so let's find these probabilities for both states. So P0, the probability of finding a molecule in state 0, is going to be well, since epsilon I is 0 in the case when I is 0, the ground state has an energy of 0, then the numerator here just becomes 1. And remember down here, this epsilon does not have a subscript I on it. This is the spacing, effectively. All right, so that's the probability to find a molecule in state 0. How about the probability to find a molecule in state 1? Well, now epsilon I becomes epsilon in the numerator. So this numerator is e to the minus beta epsilon over 1 plus e to the minus beta epsilon. Okay, so now let's look at the limiting cases for the temperature. As the temperature goes to 0, we already know what we should expect to happen, right? We would expect all of the molecules to end up in the ground state. So let's see if that happens here. So as the temperature goes to 0, since beta is 1 over the temperature, then beta is going to infinity, which means this term, just like before, e to the minus beta epsilon is going to 0. And so the probability just becomes 1 over 1, or 1. So as the temperature becomes absolute 0, the probability that you'll find any given molecule in the ground state is 100%, as expected. And what's P1 in this case? Well, in P1, if e to the minus beta epsilon is 0, then the numerator here is 0, and the denominator is 1. So P1 equals 0. You don't find anything in the excited state. Okay, so this is basically saying all the molecules are in the ground state, which is what we expected. Now, how about as temperature goes to infinity? So naively, we might expect that as the temperature gets really hot, that we would find all of the molecules in the excited state. That would be the intuitive expectation. And you wouldn't be completely crazy if you expected that, but it turns out that that's not what happens. So let's see what happens. So as the temperature goes to infinity, then beta goes to 0. And if beta goes to 0, then e to the minus beta epsilon goes to 1. And if e to the minus beta epsilon goes to 1, then p naught is going to be 1 over 1 plus 1, so half. And p1 is going to be 1 over 1 plus 1, so a half. So now you have a 50-50 chance of finding a molecule in either state. So as the temperature gets hot, surprisingly, we don't find all of the molecules in the excited state. We find that they are equally distributed between the two states. So this is surprising, and it's really cool how we were able to arrive at this just using the partition function. It's a fairly straightforward thing to conclude for the two-state system, but it turns out that this is also true in general, not just for the two-state system. But in general, as t approaches infinity, all states are equally occupied. As opposed to all molecules being in the highest energy state, which is what you might expect. So they become equally occupied as T approaches infinity. So to summarize the partition function, the partition function describes how molecules at some temperature T are partitioned. That's why it's called a partition function. How they are partitioned among the available states. As we saw up here in this simple two-state example, depending on the temperature, we see that the molecules might be partitioned all in one state and none in the other, or they might be half and half, or anything in between. Okay, so this is a very powerful tool, and we're going to be applying this in the next video.